Alrighty. Good morning, everybody. Welcome back to Calc 1. Plan for today is we're going to finish off our discussion of Standard 2, wrap up our limits discussion, at least the limits packet, and then move on to Standard 3, start talking about continuity. As far as office hours go, I've got office hours today and Wednesday at 11 and 1, and I'll have office hours tomorrow at 1. As far as homework goes, we are going to have a quiz on Wednesday, I know what day it is, over Standard 2. And I also posted some web work problems that will be due Friday. And homework 4, which was originally due tonight, is now going to be due on Wednesday. So, Friday's class. Sorry about that. Try to get you all up early, only to disappoint you. Yeah, I woke up Thursday night. I was feeling a little bit crummy, hoping I could power through Friday. Then I woke up Friday morning, coughing up a storm, and decided no way. So I apologize for that. I kind of have baked into the semester one day of something like this coming up and being off. If we end up missing any future classes, we'll do something to make them up, which might just be me recording a video on my own for you all to watch. But yeah, I do apologize for missing class on Friday. I have stuff for you, and by stuff I mean a large pile of quizzes to pass back. So without further ado, let's see. If I call out your name, please raise your hand. It will help me, at least until I've done this a few times and know where everybody's sitting. Roten. Charlie. Lewis. Emery. Katie Clifford. Oh, that is it. Okay. So I've got three Kate/Katie's in the class. So when you immediately put your hand down, I thought it was different. Reagan, Emily, Gabe, Katie Edison. Kate Grimley.
Here.
We're by each other. Carson. Morgan Iverson. Move you up in a second. Caleb. Taylor. Jonah. Aiden Pratt. Other Morgan. Aiden Quirk. Liam. Nathan. Anna. Ty. Eden. Emerson. This class gives me a working. Nolan. Nora. James. Franklin. And I know you're not here, so I'm not even going to see you. Lauren. Everybody. Okay, so a couple comments on the quizzes, especially because this is the first quiz you got back. So, oh gosh, I forgot my own grading system for a second. So each quiz, you're going to get one of 3 grades, M, J, or N. M stands for mastery. So if you got an M on your quiz, pat yourself on the back. You earned yourself a mastery. J is supposed to stand for journeyman. And the score of J means you got close, like you had a lot of good stuff going on there, but there was something fairly important that I felt like you missed. Like it wasn't quite there. And N means novice, which N basically means there's something still pretty major that you're missing. Like you still got a ways to go on that standard. These 2 grades affect your overall grade in the same way, which is they don't affect your overall grade at all. So if you got a J or an N on your quiz, that just means you didn't get a mastery. Doesn't mean you can't get masteries going forward. There are lots of opportunities to still earn masteries on, say, Standard 1, but you didn't quite get there yet. On the other hand, if you got an M for mastery, pat yourself on the back, you got yourself a mastery. If you got up to 2 M, if you have 2 M's from, say, Standard 1 in-class quiz plus a retest, then you are done with Standard 1 for the semester. But Dr. Gerstel, I got an M- or an N+. What do these things mean? The minus, like if you got an M-, that means there's something very slightly small I didn't like. But, and that's me being nitpicky. It's my job to be nitpicky. I'm a mathematician. Mathematicians are nitpicky. But I still gave you the mastery. You got an M-. N+ is, well, you're between a novice and a journeyman. You're between an N and a J. J+, journeyman. The plus minus is just me saying, yeah, you're kind of overall between 2 scores. If you really impress me, I might give you an M+. But that would take some, what's the word I'm looking for? That would take a real impression. Nobody got an M+ on this quiz. None of you are that special. As Dr. Arndt would say. Well, he would say none of you are special at all, but I'm not going that far. Any questions or comments about my grading scheme? So something I meant to do over the weekend and then didn't because this weekend was a disaster, was updating everyone's mastery totals in Canvas. So I'll do this either later today or tomorrow, but you'll be able to go into Canvas, and Canvas won't show you, like, on this, on the in-class quiz, 1A, you got an M-, but then you took it outside of class and got a J+. Instead, all I'm keeping track of on Canvas is just how many masteries you've earned in total for each standard. So right now, if you go into Canvas, you have like 21 different grades, and they're all zeros. Once I go in and update Canvas's totals, you might have like a 1 in your Standard 1 column, or a 2 if you've earned 2 masteries. And I will personally keep like a more detailed record book for my own records of what you got on each individual attempt at taking a quiz or test or retest. But on Canvas, all that I think is really you need to know is how many masteries do you have for each standard in total. So that's what I'll be keeping track of there. Yes?
For retesting, do we like schedule with you during your office hours, or we just show up, or how does that work?
So the way I'd like to do it for retest is, in general, please send me an email to say, Dr. Ursula, I would like to retest standard blah. Can I come at X time? And then in general, I'll pretty much always say yes, as long as it's not like at a time I can't meet. So if you schedule time during my office hours, the answer will always be yes. Unless you decide to be snarky and come in and say, Dr. Ursula, I want to retest standard 10. in which case I'll yell at you and say you don't even know what that is. But yeah, in general, send me an email. Let me know what time you would like to come in to do a retest, and then you just come in during that time. I put you in the side room and you do the retest. Any other questions or comments before we get started? Some math. In that case, what type of math is most commonly discussed between seabirds? The most common type of math discussed between seabirds is inter-gull calculus. It's like integral calculus, which is what we'll be getting into in the last 6 things. Okay, so when we left off, gosh, last Wednesday, it's been a while. We were talking about how to evaluate one-sided limits, and we said that my eraser's and we said that if you put like a little minus or a little plus after the number that x is approaching inside of your limit, then that's used to indicate just the limit as x approaches a single number only from the left necessarily, or only from the right. And to indicate a limit from the left, we put x approaches a minus and say for all the values of x a little bit less than a, our y values are getting really close to L. And similarly, if we want to look at just values of x a little bit to the right of a, we say a limit as x approaches a with a little plus sign, f of x equals L. And if the left and right hand limits are both the same, then we say that the overall limit, without specifying a direction, and you know you're not specifying a direction if you just say x approaches a without the minus or the plus. If the left and right hand limits are the same, then the overall limit exists and is equal to that value L. But if either the left limit or the right limit fails to exist, then the two-sided limit, the overall limit, also is going to fail to exist. So as just a quick example, something that's not in the pack, not going to be in your packet, but as just a little bit of a reminder, we have a function that does something like this. Just for the sake of argument, this is your function f of x, and if I were to ask, what's going to be the limit as x approaches 1 from the left? We're going to be approaching a y value of 1 if we look at values of x just a little bit to the left of x equals 1. Meaning if we were to plug in values for x like 0.9, 0.99, etc., we're going to be getting y values really close to 1 here. So our limit is going to be 1. Limit from the right?
3.
Yeah, for similar reasons, if we plug in values of x that are just a little bit greater than 1, like x equals 1.01, etc., we're going to be getting y values that are really close to 3 instead. So with that in mind, it's the limit as x approaches 1 without specifying direction. It does not exist because the limit is different coming from the left and coming from the right. If I were to ask you the limit as x approaches 4 from the left? Yeah, it's going to be 2. Is what I would say if that was correct, but that is not correct. Trick question. I need to give you the function that you're taking the limit of. And then that would indeed be equal to 2. In this case, the left-hand limit as x approaches 4 would be 2, because if you plug in values of x a little bit to the left of 4, you're going to be getting y values really close to 2. Similarly, the right-hand limit as x approaches 4 would also be 2. And so the two-sided limit, the overall limit, would exist and be equal to 2 as x approaches 4. But you always got to include the name of the function in here that you're taking a limit of. Otherwise, just writing limit as x approaches 4 by itself is pure nonsense. That'd be like if you were taking your English class and you were to try and write a sentence in a paper that says, I love to. You love to do what? You're taking a limit as x approaches 4 of what? Very nitpicky detail, because obviously in this case I knew that I would probably get whoever, thank you Dave for being a good sport, that if I didn't leave this off, everyone understood what I really meant. But technically, you do always need to include the name of the function. And if you don't do that on, say, a quiz, that's going to be the difference between, say, an M and an M minus. Or if you've irritated me in enough other ways, could be the difference between an M minus and J, or J plus. Keep that in mind. So with that in mind, I wanted to look over one more page of examples before moving on to talk about standard 3, where we're going to look at continuity, what it means for a function to be continuous. And I want to look at a few different limits here that are all closely related. A limit as x approaches 4 from the right of square root of x minus 4. Limit as x approaches 4 from the left of square root of x minus 4. And finally, the limit as x approaches 4 without specifying a direction, square root of x minus 4. So go ahead, take a minute or so, talk to your neighbors and see if you can evaluate what you think each of these limits is going to be equal to. And then we'll reconvene together in a minute here and discuss what we find.
Yes, I should graphing it. So 4 of the left. Yeah, like this. And so that would be both sides would exist. Would right be so would exist? Right. That would be the row. Yeah. Okay. Alright.
Oh yeah, and that makes sense because that 3.9 numbers would give you a negative.
Right.
Yeah.
Yep, that's right. Yeah.
And then this one would be like a negative 0, so when there's that shift one. Like if you think about it, it's like
Is that first? Graphic after this class?
You do not necessarily need to graph and calculate for this class. A big portion of this class is to teach you how to do the things that you might otherwise use a graphing calculator to do, such as graph things. That's going to be a major theme about 2/3 of the way through the semester.
Graphing.
These properties of the derivative and limits and et cetera, in order to
because the name on there.
No, that is not a graph of y equals square root of x minus 4. I'll talk about this graph here in a few minutes. That would be that's a scary looking graph, and please do not make me give you a formula for that function, because I wouldn't know where to get. So, does anybody have any thoughts on how we would take a limit as x approaches 4 from the right of square root of x minus 4? So in other words, if we're going to be plugging in values of x that are just a little bit to the right of 4, like 4.1, 4.01, 4.001, what sort of outputs are we going to be getting when we plug that into square root of x minus 4?
Imaginary.
Imaginary? Gadzooks. Why is that?
Because you get a negative number, or taking the square root of a negative number.
Do we?
Oh wait, no, it's the other way. Never mind. Never mind. No, you're taking positive. You're getting positive answers.
I was going to say,
My bad.
yeah. I think you have the right thought, but for the wrong question.
Yes.
So yeah, so if we're plugging in a value of x, like 4.001, let's say, when you subtract 4, what type of number are you going to get? What's that?
Close to 0?
Close to 0. More specific. Positive or negative close to 0?
Positive.
And if you take the square root of something that is positive and very close to 0, what are you going to get?
0. A number closer to 0.
I was going to say, you're not going to get 0. Square root of a positive number is always a positive number. But you're going to be getting something that's really, really close to 0. Like if, for instance, we were to plug in, say, 4.01 for x, we'd be taking square root of 0.01, and you'd be asking yourself the question of what number do I have to square in order to get 0.01? Which is actually going to be square root of 100th, which is a 10th. But the moral of the story is, if you plug in a value for x that's just a little bit to the right of 4, you're going to be getting outputs that are going to be very small, that are going to be positive, but very, very small. So with that in mind, what would you say that the limit is going to be of square root of x minus 4 as x approaches 4 from the right? We'll try and raise an eyebrow provocatively.
Would it be 0?
It would indeed. Yeah, we're going to get a limit of 0. And we can even say if x is greater than 4, x minus 4 will be a positive number. So square root of x minus 4 will always be a positive number. But if you take the square root of a number close to 0, you're going to get an output that is always very close to 0. Take this. And so we would in fact say that the limit as x approaches 4 from the right of square root of x minus 4 is going to be 0. What if we took a limit from the left?
Then it'll be imaginary. Because no matter how close you get to 0, it will still be a negative number. Because it'll be slightly smaller than 4, and you can't have the square root of a negative number.
Gadzooks.
Or well, you can, but it's not a real number.
Yeah, so in other words, if we were to plug in some number x that's just a little bit less than 4, like let's say we plugged in 3.99 for x into this expression, square root of x minus 4, what we would be getting is the square root of negative 0.01 which leads to sadness. Because for the purposes of this class, you cannot take the square root of a negative number. Now yes, if you wanted to include imaginary numbers, you could say, but Dr. Gerstle, that's just I over 10. But we're not going to be doing imaginary numbers in this class. That being said, if you go on and take enough math classes, eventually you can take complex analysis, which is a 400 level math where we do calculus involving imaginary numbers. So with that in mind, I think I would agree and say that the limit from the left as x approaches 4 does not exist. For the reason that if x is a little bit less than 4, we'll have that x minus 4 is less than 0. So square root of x minus 4 does not exist. By the way, why can't you take the square root of a negative number?
Because when you multiply two negatives, you always get positive.
Yeah. If we had something like the square root of negative 9 is equal to some number, call it a, mathematically, that's the same as saying that a squared has to be equal to negative 9. Because in order for the square root of say, something like positive 9, which is 3, that means 3 squared will give you 9. But if you take any real number and square it, if a is positive, a squared should be positive. If a is negative, a squared should be negative times negative is positive. And if a is 0, then, well, a squared should just be 0. So, that's why you can't take the square root of a negative number, is because you'd be saying you could square some real number and get a negative thing, and that can't happen. Unless, of course, you use imaginary numbers. If you're curious, by the way, imaginary numbers comes from the fact that mathematicians saw functions like f of x equals x squared plus 9. And mathematicians always want to ask the question of, I want to make this equal to I want to be able to plug in something for x and get 0. but I can't because, gosh darn it, no matter what I plug in for x, it seems to always come out positive. And some mathematicians basically just said, well, fine, you know what? I'm just, if I can't find any solutions, I'm just going to make up my own. And surprisingly, that's led to a bunch of surprisingly useful and valid and cool and radical, etc. results in physics and and math and chemistry. I'm getting off topic here, as you can see, because this is a topic of which I have strong personal feelings. But the moral of the story is, for the purposes of this class, you can't take the square root of a negative number. And if your function's not even defined for values of x to the left of 4, the limit can't exist there. So I'm going to say square root of x minus 4 does not exist to the left of x equals 4. If we were to try and graph the function y equals square root of x minus 4, it would look something like this. 1, 2, 3, 4. Whoop. You can even see to the right of x equals 4, you're going to get y values that get closer and closer to 0. But to the left of x equals 4, there is nothing. An existential void, so to speak. Which is going to lead me to my last question. What if we don't specify a direction and just ask, what's the limit as x approaches 4 of square root of x minus 4?
Both of the sides are different, so it doesn't exist.
I would hesitate to say both the sides are different, which technically is true, I guess. But I would also say that the right-hand side, or the left-hand side, excuse me, doesn't even exist. And if the limit doesn't exist on one side, the overall limit does not exist as well. So the reason why I wanted to kind of go through this exercise is just kind of illustrate, even if you don't necessarily know what the graph of your function looks like, and if there's also, you could end up in a situation where stuff can't factor out and cancel out nicely, you can still evaluate limits like this by kind of going through this sort of thought process. Thinking, all right, what would happen if we tried to plug in a value of x just a little bit to the right of 4 or a little bit to the left of 4? What sorts of outputs would that produce? What would that suggest about evaluating the limit?
Can you explain again why it does not exist?
This one?
Yeah.
Sure. The reason is since one of the one-sided limits doesn't exist, the overall limit can't possibly exist. It's a direct consequence of this result right here. Because in order for the overall limit to exist, you have to have that the left and right hand limits are both equal to the same thing. And in this case, that's not happening. We have a limit from the right of 0, but we don't even have a limit from the left, so it's impossible to have a two-sided limit.
So is that why in the first one you did, where the limit from the left was 1 and the right was 3, you said they have to be the same limit? So is that why when it was x approaches 1, is that why it does not exist too?
Exactly. Yeah, that's exactly the same reasoning. Oh, well, slightly different reasoning. In that case, we had the left and right limits both existed, but they just happened to not be the same thing.
Okay.
So the two-sided limit doesn't exist. The other way you could have a two-sided limit, like in this case not fail to exist, is if one or more of the left/right hand limits fail to exist. And you could have a left-hand limit fail to exist in this case, like by just saying your function's not even defined to the left of 4. The other way you could have like a one-sided limit fail to exist would be like the sine of 1 over x example we saw last week, where as x approached 0 from, say, the right, the function went bananas and just oscillated super fast back and forth, didn't approach a single y value. Any other questions, comments, or concerns? that's going to do it then for standard 2. So there's one more page with some questions on the standard. I'm going to let you all do it as a few extra practice problems in case you're interested. But and I'll post solutions to them, but you will not necessarily have to talk about them as a class. So next up, we are going to be looking at standard 3, where we're going to be talking about what it means for a function to be continuous. So standard 3 is going to be the last standard before we go back to talking about average rate of change and talk about how to tweak it so that it becomes instantaneous rate of change instead. Standard 3, we're mainly going to be looking at examples of kind of an application of why do we care about limits, so to speak. And one reason that we can say why we might care about limits is because limits tell us whether or not our function is a continuous one. So when I say the words continuous function, what does your mind think of? Like, what sort of picture pops up in your head when you think of something that's continuous?
Like an unbroken line.
Like an unbroken line. Unbroken. Yeah. It's a good way to describe it. Any other words you would use to describe something that in your mind you would consider to be continuous?
Never ending.
Ooh, something that's never ending. It's continuous. It goes on forever. Yeah, that's another way that you could certainly think about it.
The amount of Marvel movies made.
The amount of Marvel movies made. Oh boy, tell me about it. How many are coming out this year? Like 5 or something?
Something like that.
Not to mention the shows.
Not to mention the, yeah, well, we throw in all the TV shows, all the gazillions of episodes. That's certainly something that you could, not actually, but think of as being more continuous than any other franchise, let's say, other than maybe Disney movies. But the moral of the story is when you think about continuous things, you think about things that are unbroken, unchanged, that are kind of nice, smooth, and well-behaved, especially when you think about it in regards to functions. And so what I'm going to do in this standard is to come up with a definition that uses kind of what we built on in standard 2, that uses limits in order to concretely define continuity, and then we're going to look at a bunch of examples and see if we can determine whether or not those examples have this continuity property or not. So to start off, I'm going to say that why am I writing limit already? F of x, we're going to say is continuous at x equals a. I'll write out the word continuous on the board for you once. It's the only time I'm going to do it all semester. Yeah, no, that says continuity, not continuous, so I haven't broken my promise yet. Usually I'm going to write out CTS. CTS is shorthand for continuous. And a point x equals a, if the following 3 conditions hold. You have to have 3 things happen in order to have continuity. First, you need that f of a is defined. Meaning, if you plug in a, whatever a is, could be like x equals 2, x equals 4, x equals negative 5 billion. it needs to be the case that if you plug in that value into the function, you get an output that makes sense. So another way to say this would be that A is in the domain of f of x, meaning it's in the set of all the valid inputs into your function. Second condition, we need that the limit as x approaches A of f of x has to exist, which means that if you take a limit from the left and a limit from the right, they come out to the same value, and that value is a number and not D and E. And finally, last condition, you need that these two things are equal to each other. You need that the limit as x gets close to A of your function is equal to what you would get if you just plain old plugged in A into your function. So in other words, what this third condition, and the third condition is really kind of the meat of the matter, is saying that what you get if you plug in values of x that are close to A is the same as what you would get if you actually plugged in A itself into the function. Activity time. So in your packet, at the bottom of the page, you may have noticed I drew out this monstrosity of a function for you. And I just kind of hand drew and scanned it in. What I would like for you all to do is to look at this graph and see if you can tell me, are there any values of x for which this function fails to be continuous? Hint, there's at least one. So go ahead, take a few minutes, and as always, you're encouraged to work with your neighbors, talk to the people sitting around you, and see if you can find all the different values of x where you claim this function is not continuous. And moreover, at each of those values of x where you say the function's not continuous, give me a reason why it's not continuous. Or your reason why I want to be one or more of these three things. So go ahead, take a couple minutes, talk to your neighbors, and see what you can make of this. Where does this function fail to be continuous?
These two.
Yeah, because additions of the positive and the additions of the negative infinities.
Right, so okay, and then this one's that continuous we'll see, I
I labeled the x and y coordinates to make it a little easier for you.
This too. Yeah. And then. Yeah. I think 0 is also.
Like you get a limit that exists. Like -3 is defined, but x doesn't equal.
Okay, that's okay.
Or -3.
And then 4.
-3.
Oh.
Or -2. Is that -2? The first one.
Yeah, that's what I thought.
Yeah. Actually, I think.
I've made many Heavy mini spiral cycle, whatever you wanna call that in my
So it's,
math days.
but no, it's for those
But-
one,
It
those
doesn't
two,
have a
but these
limit
two
in
aren't equal to each other. So it's not close.
Or is that true? I think so. Okay.
Cause I think it's still like on this function.
Yeah, okay. And then again, it's.
Or two of these for the third, right? Oh, the two different.
Yeah.
These doesn't like
So let's come back together now. So looking at this graph, is anybody able to find a value of x at which they would like to make the claim this function is not continuous? At x equals -1. Okay. So you're saying there's some funny business going on at x equals -1. So which of these three conditions fails to hold at -1?
Number one.
Condition 1, f of -1 does not exist? I would agree. If I look at x equals -1 here, I do not see any sort of indication that I could plug in -1 into this function and get an output that makes sense. So we could say that x equals -1, f of x fails to be continuous since f of -1 does not exist.
When x equal to -2, the limit.
Hold on to that thought for just a second. I have a couple more thoughts on what's going on at -1 first before you move on to a new one. Does condition 2 hold at x equals -1? Doesn't look like it. Limit as x approaches -1 of f of x, I would also say, does not exist. Reason being, looks like the function behaves very differently from the left to the left of -1 than it does to the right of -1. By the way, what would you say that the right-hand limit is as x approaches -1? Meaning if we plug in values of x that get closer and closer to -1 from the right, what sort of outputs are we getting?
Positive.
Yeah, we're getting outputs that are positive and are getting more and more and more and more and more and more, etc. Going on forever, positive, meaning that we can actually say, for instance, that the limit as x approaches -1 from the right is actually going to be positive infinity. When we say that the limit is positive infinity like this, we don't mean that like infinity is a number that our y values are getting close to. What that really means is we're just saying they're getting more and more positive without bound. there's no upper limit on how positive our y values can get if we plug in values of x just a little bit to the right of negative 1. How about limit as x approaches negative 1 from the left?
Negative infinity.
Yeah, for very similar reasons. As x gets closer and closer to negative 1, we're going to get y values that are getting more and more and more and more negative, more and more down through the floor. I can't say that, I would get fired. Negative infinity. Question? Okay, sorry, I was looking like a little bit of a hand. So, these are not the same. Limit does not exist at negative 1. Also, f of negative 1 does not exist. And we could also even say condition 3 fails because in order for these two things to be equal, they would have to exist. And two things that don't exist can't be equal to each other. So, basically everything that can go wrong at x equals negative 1 does go wrong at x equals negative 1. And so we would say the function is not continuous there. What's your name again? Aiden. Sorry. Aiden, it sounds like you had another value of x in mind that you wanted to propose.
X equals negative 2, it fails rule 3.
At x equals negative 2. So, yeah, there's some, doesn't look quite as scary as x equals negative 1, but there still looks like some funny business going on at x equals negative 2. Does f of negative 2 exist? I would say so. I would say f of negative 2 is equal to positive 2. Because if you go to negative 2, we have a filled in dot up here too. How about a limit as x approaches negative 2 of our function? Does our function have a two-sided limit there? I would say so. Looks to me like as x gets close to negative 2 from either the left or the right, we're going to get y values that approach 1. So condition 1 holds, condition 2 holds, but condition 3 does not hold, since these are not the same value. Limit as x approaches negative 2 does not equal f of negative 2. So our function is going to fail to be continuous at negative 2. Yeah, good finding, I agree. Are there any other values of x at which you said this function fails to be continuous? James?
At x equals 0.
At x equals 0, what's going on there?
So first off, f of a is not defined. Or f of 0 is not defined.
It's not. Gadzooks. Certainly appears that way. So right away, condition number 1 is going to fail. And that automatically implies condition 3 is going to fail as well. Then condition 2 will check out at x equals 0, because the limit does exist at 0. You get a limit of 2, but f of 0 does not exist. So I think we are out of luck there. And we only need one of these 3 conditions to fail in order for the function to not be continuous. Anybody else? Were there any other values of x y'all found?
X equals 2.
X equals 2. What's going on at x equals 2?
Fails rule 2, the limit does not exist on both sides.
Golly. The limit doesn't exist on both sides?
It's not equal.
So
on the left it's getting closer to y is 2, or f(x) is 2, and from the right it's -1. So the limit is x equals 2 does not exist.
Yeah, I think at x equals 2, condition 1's going to check out because f of 2 exists. It'll give you -1, or at least it would if I drew this in a less haphazard manner. But the limit from the left is not equal to the limit from the right, so the two-sided limit does not exist. So it's going to fail condition 2. So we could say that the limit as x approaches 2 from the left does not equal the limit as x approaches 2 from the right of our function. So so the overall limit as x approaches 2 does not exist. Which means x equals 2 is yet another point where our function fails to be continuous. Any other values of x? X equals 1. Ooh yeah, looks like a sharp point to our function at x equals 1. And if there's one thing I want you to take away once you're done with calculus, it's that sharp pointy things are bad. Good pro tip for life as well. So, what's going on at x equals 1? Why did you throw that out there?
I don't remember why, but I just know that cusps are discontinuous.
So let's see. And this is going to be an example of something called a cusp, which we'll define more precisely later on. It certainly looks, so first of all, does f of 1 exist? Sorry. Question or comment?
No, I'm
Okay, you insist. Does f of 1 exist? Yeah, let's say f of 1 is 0. Does the limit as x approach 1 of f of x exist? Well, as x approaches 1 from the left, it looks like we're going to get y values close to 0. As x approaches 1 from the right, it looks like we're going to get y values close to 0. So I think we get a limit of 0. Does f of 1 equal the limit of the function as x approach 1? Well, we said both of those are 0. X equals 1 actually checks out. It's an example that f of x is actually going to be continuous at x equals 1. Now you are right that there are some shady business going on at x equals 1, and it's going to turn out to be the case that f of x is not differentiable at x equals 1. But you can have a function that is continuous at a cusp like this. Cusps are okay for continuity. It's going to be another condition we'll talk about in a future standard called differentiability that's going to be broken by the fact that we have a sharp corner / cusp thing going on at x equals 1. But these three conditions all do check out at that point, even though the function is a little bit wacky there. Anybody else have any other points they would like to propose for a point where f of x fails to be continuous? Me neither. I think these are the four where bad things are happening. By the way, thanks for mentioning x equals 1. I purposely put a cusp in there to see if anyone would bite at it, and I was hoping someone would, so that we could have a discussion about how continuity can still work at points like that. That's a little bit of a trick question, but one that I put in there to make a particular point. If you haven't figured it out yet, I love me some trick questions. Not on like quizzes or exams or anything, but just in class. A, because it helps me to make a point, but more importantly, B, it makes me feel smarter at your expense. I'm all for that, because I have a very fragile ego. So So these are going to be kind of like a collection of ways in which you can have functions that fail to be continuous. The function exists and the limit exists, but they're not the same. Both the f of x and f of a and the limit don't exist. The limit exists, but f of a does not. F of a exists, but the limit doesn't exist because it's different from the left and right. And excuse me, point like at x equals 1 where you have a cusp, but it still checks out because the limit still exists and is equal to the value of the function. Any questions, comments, or concerns relating to this graph? Intuitively, you can sort of think about what does it mean to say that this function is continuous at a point by saying, you may have heard back in the day from your teacher something along the lines of, oh, you can draw the graph of the function without having to lift up your pencil or your pen or your writing implement of choice, your quill. And you can sort of see at x equals -2, x equals -1, x equals 0, x equals 2 are going to be the points where if I were trying to trace this out on the board, I would have to sort of pick up my piece of chalk to do something else, to do something different. Whereas at a point like x equals 1, I don't have to lift up my chalk off the board in order to draw that one. So that kind of gave like grade/high school level definition of continuity is maybe intuitive, but a little bit imprecise. Because, I don't know, mathematicians don't like kind of sloppy language like, oh, you don't have to pick your chalk up in order to draw this. That may work as sort of like a working, intuitive definition of what's going on, but it's not very mathematically precise. For instance, what if you weren't writing in chalk? What if you weren't writing it at all and you were just picturing this image in your head of a function? This beautiful, beautiful image. So having like a more precise definition of continuity like this is something that mathematicians often will strive for. And this kind of gives us a way to make that a little bit more precise, is to introduce the notion of limits in talking about continuity. Then I want to do another example. All right. Have a good one, everybody. When we come back on Wednesday, we'll have the Standard 2 quiz, and then we're going to look at some more examples of continuity, in particular, focusing on piecewise functions. Y'all have a good one. And if you want to do a retest on Standard 1 or Standard 2 at this point, send me an email and we will get that set up.